Now we're going to change gears and dive into some spectral processing, and this is going to set the stage for the rest of the day, where we can start to learn a little bit about the fundamentals of NMR data processing, which will then help us start to approach non-uniform sampling and reconstruction. So Frank, if you are ready and you've got your mic unmuted, I'll turn off and let you take the stage.
Great, very much. Things sound okay? Things look okay, Adam?
Yes, perfect. Looks good, sounds good.
Excellent, thanks so much. That was an awesome introduction. NMR Box is what I would say the most incredible and useful software resource that we have in NMR, and it keeps getting better, as we've seen. Lots of folks have contributed to the work that we're going to see, including all of the NMR Box staff that we've heard from today and will hear from during the week. Today, I'm going to talk specifically about NMR spectral processing and analysis. And in particular, I'm going to talk about the relationship between the time domain and the frequency domain and how we move between them. So this is a familiar view of NMR. Everybody in the audience knows about it. We measure a time domain signal, and we use the Fourier Transform to convert that time domain signal into a spectrum. Now, from an information content point of view, the time domain data and the frequency domain data have the same information in it, just rearranged in a different way. And for sure, as we'll see, there are many mathematical operations that are easier to do in one domain or another. And from a visual point of view, in particular, there are some reasons that we prefer one domain over another. And it's kind of instructive and interesting to look at a generic example of this to drive the point home. Okay, so what you see here on the left is a color picture. It happens to be a picture of a tarot card. And on the right-hand side is a histogram of the colors in this image. So in other words, we could think of this histogram of colors more or less like a spectrum. And this picture has lots of light and dark blue. So the histogram of colors, which you can see over here, has lots of light and dark blue. And in this image, person holding onto a wooden staff that's mostly red, and there's a little bump in the red area of this spectrum. So what is this good for? What can we do with a spectrum, even if we don't know much about what the spectrum itself means? Well, here's an example. Let's pretend we have a database of spectra, like the kind shown at the top of the screen. So our little database of spectra consists of spectra A, B, C, and D, all right? And then at the bottom, we'll have an unknown spectrum. So feel free to unmute yourselves and say which of these four spectra in the database is a closest match to this unknown spectrum X. And we can make it even clearer if we color the spectra according to the hue that the histogram represents. So lots of people will look at this and say it's D. Spectrum X matches spectrum D most closely. And I'd say that too, even if we don't know what the underlying information is. So each of these spectra is the spectrum of a picture in this case. So let's see what they are. Well, spectrum A is a picture of the Burger King. Spectrum B is the spectrum of a picture of Don King. Spectrum C is a spectrum of a photograph of the Lion King. And spectrum D, likewise, of the Tiger King. So what did we actually see? The numbers that are reported here are the amount of overlap between these four database spectra and our unknown spectrum X. And spectrum X overlapped at 61% with this spectrum D, more than all the others. So just by comparing the shapes of these spectra, we could identify the most closely matching image feature. And it turns out that this unknown spectrum X is a photograph of a big artwork on a wall that somebody spray painted here. And just based on color matching, we could identify an image in our database with the unknown image X, just by spectral matching, okay? So congratulations, everybody has just done an exercise in visual spectral matching. And this is why we convert time domain data to frequency domain data, because it makes it easy for us to analyze visually. So let's talk in more specific detail about NMR data itself. So we know in the one-dimensional case, somewhere we have a pulse in our pulse sequence that stimulates the sample, and then we have a radio antenna and we listen for radio waves that come off the sample. And generally, we digitize and measure these radio waves at discrete sampling points that are uniformly spaced in time. So one-dimensional experiment. In the case of a two-dimensional experiment, somewhere in our pulse sequence, we have a pair of pulses and an evolution time between them that varies in a systematic way. And at each one of these evolution times, we measure a different 1D NMR experiment. And after we accumulate a collection of experiments like this, first we Fourier transform all the rows of this collection to generate an interferogram. And then we Fourier transform all the columns of this interferogram to generate a spectrum. So what does that mean? The nature of this kind of acquisition scheme means that every signal in one dimension is modulated in some way by a signal in the other dimension, the indirect dimension. And so if we look at a mathematical description of any individual signal in the two-dimensional data, what we find is that even though it's a two-dimensional matrix, the signal comprises a two-dimensional matrix, we can describe everything about this two-dimensional matrix in terms of the products of one-dimensional profiles. So in the time domain, a signal can be described as the product of a one-dimensional time domain profile in one direction and a one-dimensional time domain profile in the other, and the product of these two forms a two-dimensional matrix. So all the points in this two-dimensional time domain matrix are not independent of each other. They're related in this special way as the product of one-dimensional profiles. Now, when we Fourier transform all the rows of this matrix, we get an interferogram. And even though the interferogram looks different, the information content in it is exactly the same, and it can still be expressed as the product of one-dimensional profiles, except now one of these one-dimensional profiles is a frequency domain profile, a line shape, and the other is still a time domain profile. And the product of these two gives us the interferogram. And so finally, when we Fourier transform all the columns of this interferogram, we get a new matrix. This matrix has the same information content as the previous two, and this matrix is also expressible as the product of two one-dimensional profiles, but now they're both frequency domain line shapes. So we have a line shape here and a line shape here, and the product between these two line shapes gives us our two-dimensional matrix of intensities. So here in the time domain, we have a signal that extends substantially throughout the whole 2D matrix. And when we Fourier transform it in one dimension, we've concentrated the signal into one band. So now we've kind of simplified the spectrum and made more empty space. And likewise now, when we Fourier transform all the columns, we've localized the signal in both dimensions. So Here we go from a signal that's hard to analyze by eye and extends throughout the whole data. And we've converted it into a signal which is largely localized, and we can analyze it by eye. We can see clearly where it is in frequency space and see about how broad it is in the 2 dimensions. So this is what it looks like for a single theoretical signal. And here's what it looks like for an actual measured spectrum down at the bottom. How does this all work? As we mentioned, in both the directly detected dimension and the indirect dimension, we're acquiring data where some time increment is uniformly spaced. And there are 2 parameters of interest. So the spectral width that we can measure depends on the spacing between adjacent points that we sample. And the more finely spaced that we get these points that we sample, the broader, the wider the spectral width that we can accommodate. And based on the distance in time between the first point that we measure and the last point that we measure, we place an upper boundary on the achievable resolution of the measurement. So in other words, the resolution of the measurement depends on this time distance between the first point and the last point. Why is that? Let's see. Let's consider 2 signals that are almost the same. They're at almost the same frequency. Here's what they look like in the time domain. Here's what they look like in the frequency domain. One is blue, one is red. So as you can see, they're kind of hard to distinguish in both of these cases. But as we acquire more and more points over a longer and longer duration, the difference between these 2 frequencies becomes more and more apparent. And this explains in a very simple way why we need longer duration to distinguish finer and finer differences between frequencies. Now, one of the ways that we can use to reduce measurement time while retaining the achievable amount of resolution is non-uniform sampling. And we're going to talk about this in detail today. In non-uniform sampling, we conduct a traditional multidimensional experiment where we have a set of time increments that are incremented in a regular way. But then randomly, according to some pattern, we skip over some fraction of the measurements. And so since the amount of experimental measurement time we need depends on the number of 1D increments that we measure, the experimental measurement time is reduced. But since the achievable resolution depends on the time difference between this first time domain data that we can measure and the last, we can retain resolution, as we will see. But what's the challenge? We've already seen in conventional data, we can go from time domain to frequency domain data by a set of Fourier transforms to generate a spectrum. But in the case of non-uniformly sampled data, we can Fourier transform all the rows and we get an interferogram. But this interferogram has gaps in it in the indirect dimension, in the places where we skipped over acquisitions. And so when we Fourier transform the columns of this non-uniformly sampled interferogram, we get a spectrum, but it's not a very good spectrum. So for example, here's a 2D proton-carbon methyl spectrum of a monoclonal antibody at natural isotopic abundance, so pretty remarkable actually. Here's a conventional 2D measurement, and here's the Fourier transform of a non-uniformly sampled version of that measurement that included only 50% of the increments. So you can recognize it as a spectrum, but it's full of these crazy artifacts that we'll talk about in more detail. So if we use a regular Fourier transform, we get a result like this, which isn't great. But as we will see, there are a number of different reconstruction methods that we can use to generate a nice looking usable spectrum from the non-uniformly sampled data, which for all intents and purposes is generally as good as the conventional data, except this spectrum on the right took half the measurement time compared to this spectrum on the left. So pretty cool. How does it work? Well, as we mentioned, the achievable resolution depends on the difference in time between the first point that we acquire and the last point that we acquire. So even if we skip some fraction of the measurements in between, the maximum achievable resolution is still conserved. And what we have to do is address these missing points. Now, in a conventional data set, we have our measured spectra, and then we do zero filling, and we Fourier transform the data to get a spectrum. In the case of our non-uniformly sampled data, we have a subset of the samples that are missing. And by one mechanism or another, either directly or indirectly, we have to find a way to replace the missing data in a procedure that we call interpolation. But generally speaking, any procedure that we use to interpolate, to replace missing data inside the measured parts of our time domain points, we can also use that same procedure to replace zeros that are appended at the end of our time domain data. So as we'll see, the reconstruction methods that we apply to reconstruct non-uniformly sampled data can also be used to extrapolate data. And if this is the case, as we'll see, then the reconstruction methods that we apply to non-uniformly sampled data to interpolate them can also be applied to conventional data to extrapolate them. And the purpose of that is that when we extrapolate data, we've increased the effective distance in time between the first point and the last point that we have. So we're going to be able to generate spectra with larger apparent resolution. And we will see examples of that shortly. To understand how all these things work, the best place to start is with an understanding of the Fourier transform. So that's what we will take a look at next. Now, as we've discussed, our NMR data is measured in discrete points. And to convert it into a spectrum, we use the discrete Fourier transform, which is listed up here. So the data that we want to Fourier transform is the function little x of t. The spectrum that we generate is big X of f. And to generate one point in this spectrum, we multiply our time domain data, little x of t, by a Fourier term, and we add up all the points. The Fourier terms have a real part and an imaginary part. The real part is a cosine term. The imaginary part is a sine term. And for each one of these Fourier terms, which has a different frequency, that Fourier term corresponds to a different position in the corresponding spectrum. Very simple. So let's look at the Fourier transform in a little more detail. And as we've just seen from the Fourier transform equation, the Fourier transform has real and imaginary components, but for simplicity in the following examples, even though all the math is going to happen with complex data, real and imaginary, I'm only going to show the real part for simplicity. So let's say we have some time domain data that we would like to Fourier transform. in order to form a point from the Fourier transform, we'll start with a Fourier term. We'll multiply our time domain data by that Fourier term, and that will generate a product. Okay. Now, in the subsequent slides, what I will do is monitor the amount of positive intensity in the product and the amount of negative intensity in the product by two little bar charts on the side. And generally speaking, when you multiply together two different sinusoids to generate a product, the product will have exactly balanced amounts of positive intensity and negative intensity. And so when you add up all the points of a product like this, it'll be close to zero. So when we actually go through the Fourier mechanism, for each Fourier term, we multiply our time domain data by that Fourier term to generate a product. And then we add up all the points in that product to generate 1 point in the Fourier transform. And what we see is it's only in cases where the frequency of the Fourier term matches one of the frequencies in the time domain data that we get a product that's either predominantly positive or predominantly negative, so that when we add up all the points in the product, we get a non-zero sum, which results in a peak in the corresponding Fourier transform. So it's a beautiful and simple mechanism that matches frequencies in the time domain data with frequencies of the different Fourier terms. So pretty awesome. And in fact, the nature of this analysis lends itself to mechanical interpretations. And over time, people have built different mechanical tools to perform a Fourier transform by using gears of different diameters to represent the different Fourier frequency terms. So this is kind of fun. There are a lot of examples of these machines on YouTube and so on. If you have an idle moment, I encourage you to take a look, because there's an incredible amount of clever math and engineering that went into building devices like this. But to return to our emphasis, which is applying the Fourier transform to biomolecular NMR data, typical circumstance is in the indirect dimensions of biomolecular spectra is that we can only measure data over a limited duration, and generally that data doesn't decay much, so we measure it over a certain period and it's truncated. So what happens when we have data like this that's truncated and we use our Fourier transform mechanism? Same deal as before. We have our Fourier term and we multiply it by our truncated time domain data, and that forms a product which is also truncated. And since this product is truncated, when we add up all the points, we no longer get perfect cancellation between the positive parts of this truncated product and the negative parts of this truncated product. And the end result is, when we look at the corresponding spectrum, it has these truncation wiggles. Okay. Let's see, people are waiting to get in, sorry. So, truncated data, we don't get a nice narrow spectrum anymore. We get this broad spectrum and these truncation wiggles that start out big close to the peak and get smaller as we move further away. Now, the usual remedy for this problem is to apply a window function that we also call a digital filter or an apodization function. But using a window function is a compromise. We can use a window function that broadens the lines to reduce the artifact at the expense of reducing the signal. Or we can use a line sharpening window that sharpens the line, but at the expense of increasing the artifacts. So this is a challenge, and we often use a compromise of these two. Not ideal, but how non-ideal it becomes actually depends on the number of points very critically. So here's some examples of line shapes that we get from some different window functions. This is with 32-point data. But look what happens now if we have 32-point time domain data. And in this case, all the time domain data is simulated. It has no noise in it whatsoever. They're ideal signals. So 32 points, we can get spectra like these. But if we have only 8 points, even if the underlying signal is exactly the same as it is in these cases, when we Fourier transform this 8-point data, we get ridiculously broad apparent lines and these large artifacts. Okay, so this isn't great because the shape of the spectrum that we observe is related mostly to how we performed the reconstruction rather than to any underlying property of the time domain data. So that's not great. We don't want a spectrum that depends mostly on the reconstruction method. We would like a spectrum that reflects the nature of the underlying signal. So the most common remedy for that previously has been the method of linear prediction. We extrapolate the data. And as we discussed before, when you extrapolate data, you can increase the apparent resolution. Linear prediction works in a two-step procedure. First, by building what's called the linear prediction model, and then using that model to extrapolate the data. The linear prediction model says that we'll take a certain number of points from the time domain data, let's say 4 points, and we will make a linear combination of those 4 points in order to predict the next point in the time domain series. And it turns out that this method of prediction, by predicting a given point as a linear combination of previous points, is exact for exponentially dampened sinusoids. So the linear prediction model has special relevance for us in NMR. So in the linear prediction model, we find one set of coefficients such that, for instance, when we use them on the first 4 points to predict the 5th point, or the next 4 points to predict the 6th point, and so on, when we set that up, that gives us a set of linear equations that we can solve by the usual methods to find what the best values for these coefficients are. And then once we have them, we can take these coefficients and apply them to the last points in the time domain data. So in this case, the last 4 points in the time domain data. And we use these coefficients to make a linear combination of these last 4 points to generate one new synthetic point that we add onto the data. Then we can take our 4 coefficients and slide them over and use the last 3 measured points and our new synthetic point to predict yet another synthetic point. And then we can slide the coefficients over again and predict a new synthetic point and another new synthetic point, and so on. And we can actually do this indefinitely. We can append as many synthetic points as we want to the data by this method. But in practice, the experimental data has noise in it. So these coefficients aren't perfect. And also, since the experimental data has noise in it, even if the coefficients were perfect, when we apply them to the last points in the data, which have noise in them, to predict a new point, that new point will have some error in it because of the noise in the final points in the data. And so any of these errors that are directly in the coefficients or in the experimental data, those errors will propagate and get larger and larger the more synthetic points that we add, which places a practical limit on the number of synthetic points that we can add. So generally speaking, we try to only double the number of points by this linear prediction procedure so that we don't have more synthetic points than actual data points. And we also know later when we process the data, we're commonly going to use a window function that will de-emphasize these synthetic points anyway, so they'll be slightly less important than the measured data. So that's linear prediction. Here's what it looks like in practice. So our original spectrum, here's what it looks like if it's inverse transform. Here's the part that we add on by linear prediction extrapolation, so that when it's Fourier transformed again, we have a sharper line. Here's what it looks like on 2 dimensions, the 2 indirect dimensions of a 3D data set. Here's a plane from a CB, CA, and H. And here's what the corresponding plane looks like when linear prediction is used in both indirect dimensions. So it's a pretty easy way to get a reduction of usually 20 or 30% at least of the line widths in the 2 indirect dimensions, which is very handy, and it's not too difficult to do. As we'll see though, there are deficits to the linear prediction extrapolation method, and we can get improved results if we use non-uniform sampling reconstruction methods to do this extrapolation instead. So let's get to that. Talk about how to reconstruct non-uniformly sampled data. There are many approaches for reconstructing NUS data. You can find most all of them on NMR Box, and there are a few that we have special facilities inside NMR Pipe to help you use directly, including the ones that are listed up here that we'll see a little bit more about today, including SMILE, NESTA, HMSIST, and the Roland NMR Toolkit implementation of maximum entropy reconstruction. So, reconstruction of our non-uniformly sampled data. Let's say we have our non-uniformly sampled time domain data to Fourier transform, and we know that that data has gaps in it. To apply a Fourier transform to data like this, it corresponds simply to filling in all the missing places with zeros. Okay, so what happens when we take data like this through the Fourier transform mechanism? Well, we saw before with truncated data that because the data is truncated, the product that we generate between the time domain data and the Fourier term is also truncated. And so when we add up all the points, we don't get ideal cancellation of the positive and negative intensities. So we get a spectrum that has these regular truncation wiggle artifacts in them. On the other hand, for the non-uniformly sampled data, we multiply our Fourier term by our data, which has gaps in it, and that forms a product which has gaps in it. And so again, when we add up all the points in this product, which has gaps in it, we also no longer have ideal cancellation between the positive and negative parts of the product. So we don't get a perfect spectrum. But instead of these regular truncation wiggles that we see in this case of truncated data, the pattern that we get looks very much like random noise. However, it is not random noise. It is a completely deterministic pattern that depends on the pattern of points that we kept and skipped in this non-uniform sampling measurement. Why do we bother to do that? We look at the points and results side by side. If we have nice continuous data and we do a Fourier transform, we get a sharp signal with a flat baseline. If we truncate data and Fourier transform that, we get a fat broad signal with regular truncation artifacts. If we have our non-uniformly sampled data and we Fourier transform that, we have a nice sharp signal, but we have artifacts of a different kind that look like random noise. Now, these artifacts, the ones that look random or these systematic ones, they are both sampling schedule artifacts. And every peak in their corresponding spectrum will have the same artifacts. So for example, in a spectrum like this one, a big peak will have big truncation wiggles that are shaped like this. A small peak will have exactly the same truncation wiggles, but they'll be correspondingly smaller. Likewise, every peak in this NUS spectrum will have this same pattern of distortions. They'll just be big for big peaks and exactly the same pattern, but smaller for small peaks. We can take advantage of this in using a reconstruction method. The reconstruction method that takes advantage of this is called iterative soft thresholding, or IST. And it takes advantage of the fact that the size of the sampling artifacts is proportional to the size of the signals. So what we do is start with a regular Fourier transform of our non-uniformly sampled data, which has these artifacts in it, and we start with a corresponding blank spectrum. And we choose a threshold, which we know is guaranteed to be above the largest of artifacts that we can expect. And we transfer a little bit of the intensity of the signals above this threshold into a secondary spectrum like this. And then once we've reduced the spectrum in this way, we inverse transform it back into the time domain. Any of the points that were skipped in the original acquisition, we set those points back to 0. And then we Fourier transform it back into the frequency domain, choose a new threshold that's lower than the previous one, and repeat this procedure over and over again. And so what we gradually do is transfer intensities from the original data to this accumulated IST spectrum. And as we transfer intensities from the original data, because the overall intensity gets lower and lower, the corresponding artifacts gradually get lower and lower too. And we can stop these iterations at any point that we like, and any residual that's left over here, we can add into the final result to ensure that it captures all of the intensity that we started about. So it's a very simple procedure, easy to understand. It works very well, and we'll see several examples of it during the course of the day. Another method that we're going to see and talk about in more detail is the method of Jinfa Ying called SMILE. SMILE is a parametric method that decomposes a spectrum into sums of line shapes that are generated from ideal descriptions in the time domain and Fourier transformed in the same way that experimental data is. So as we've discussed before, the line shape that we observe in a spectrum depends both on the sampling schedule and number of points, as well as the intrinsic signal properties, like the amount of time domain decay. So what SMILE does is it begins by building a library of different ideal time domain signals and what the actual Fourier transforms of those time domain signals look like subject to the particular sampling schedule that was used for the experimental data. So that SMILE can inspect the experimental data, and whenever it finds a signal, it can estimate the line width of that signal in the spectrum and then figure out which time domain decay corresponds most closely to that signal. And then over and over again, whatever signal is left in the data that's largest will get approximated in this way. And we'll see it in more detail, but SMILE in this way can fill in the blanks and gradually reduce all the artifacts in the NUS reconstruction. So why is this useful? Well, it's useful for both non-uniform sampling and conventional data, because this same method that we use to interpolate in non-uniformly sampled data, we could use to extrapolate spectra. Now, linear prediction that we've described before is applied individually to one-dimensional vectors. So for example, in this two-dimensional case, it would be applied individually through each vector in this peak. Now, linear prediction and all of these other methods are nonlinear methods, meaning that they behave differently when you apply them to a signal or a signal plus noise. And they also apply differently to a small version of a signal compared to a larger version of that signal. And so in the case of linear prediction, we get slightly different results when we get a vector that's through the tail of a peak where intensities are not as strong compared to the results that we get, say, when a vector is right through the most intense part of a peak. And so as a result, when we use linear prediction, we can get nice reduction in line widths, but generally at the expense of distorting the line shape around the base of the peak. And this happens, again, because this is a nonlinear method that's applied independently to one-dimensional vectors. Whereas all the NUS reconstruction methods are multidimensional. So if we apply a method like IST or SMILE to do this extrapolation, we can get much nicer line shapes. Here's what this looks like with a three-dimensional case, okay? So here's some data from a 3D N15 NOE. Here's what things look like with a conventional Fourier transform of the data, a couple of strips from that spectrum. Here's what results look like if we use linear prediction on 2 dimensions of the data. And here's what it looks like if we use IST to do that extrapolation. So better results in each case. This also works in 4 dimensions. So here's planes from a methyl-methyl 4D NOE. Here's what the Fourier transform looks like. Here's what linear prediction looks like in 3 dimensions out of 4. And here's what an IST reconstruction looks like. So much better reduction of the artifacts in the spectrum when we do it this way. What we will see generally is that for typical applications, most all of the commonly used non-uniform sampling reconstruction methods give fantastic results. And here's a simple example. Here's some data from a CBCA-CO-NH experiment. Here's what the uniformly sampled data looks like with a regular Fourier transform. Here's what that data looks like with linear prediction applied to the 2 indirect dimensions. Now, all the remaining results are extrapolation versions by IST, SMILE, NESTA, HMS-IST, and Maxent reconstruction from the Roland Nmr toolkit. They all give outstanding results and nice separation of the underlying partially resolved signals. What we are also going to see is that we have a nice graphical interface that will make it super easy for us not only to use any of these reconstruction methods, but to compare their results side by side. We'll see more about that. Now, about the behavior of non-uniform sampling, I'm going to show a couple of examples for us. One is derived from small molecule analysis, and the other is derived from a biomolecular application, but they both show some interesting information that it's good to keep in mind. So here's a 2D proton carbon spectrum of a bile acid, all right? And this particular example was measured with 1,024 increments in the indirect dimension. And to highlight what's going on with the spectrum, we're going to look at a little doublet of peaks down in here that's drawn in an expanded view over here. Okay, so, and this is, this data was measured by our colleagues at Pfizer, Greg Walker and Kathy Farley. So our conventionally measured version of this spectrum takes about 4 hours to measure if we measure 1,024 increments. So here's that data, full measurement of 1,024 increments where we can see nice separation of this doublet. If we only measure the first 128 increments of the indirect dimension, this is the spectrum that we get, and we can no longer see separation in this little doublet. So this took about 4 hours to measure, this took about half an hour to measure, but we don't have the resolution that we did in the original measurement. So this is a non-uniformly sampled version of the measurement. This also took only half an hour to measure. It used this Bruker-generated non-uniform sampling schedule. And when we reconstruct this with IST, we can get a beautiful spectrum with excellent separation, even better, in fact, than the regular Fourier Transform spectrum of these two peaks. But we did it in a half an hour instead of 4 hours. Now, for pharma people, this is a great improvement because a measurement like this has to be done overnight, but a measurement like this can be delivered in the same day, which is a substantial advantage in a pharma environment. So this is Bruker's schedule that's weighted according to one particular method and reconstructed by IST. Here's an example of the same case reconstructed by SMILE. Excellent results, no big difference. Here's the same data, but resampled with a weighting schedule, a non-uniform sampling schedule that samples heavily at the beginning and end. Okay, corresponding spectrum also looks beautiful, reconstructed by IST, no huge difference. Here's a measurement with a different non-uniform sampling schedule. This one is sampled densely only at the beginning, and we still get an excellent spectrum with nice separation. So in fact, in all of these cases, we didn't see a huge difference with respect to the choice of sampling schedule. Why is that? Well, if we look at the underlying signal in this experimental data, it doesn't decay at all. It hardly decays by less than a third. So it doesn't really matter which of these sampling schedules that we use, they all capture about the same amount of intensity. So there's less of a difference between the different sampling schedules than you might guess at first. Now, the different reconstruction methods do behave differently with different sampling schedules, but there is one important thing to keep in mind. And honestly, this point is somewhat confused in the literature, okay? Here's the Fourier transform of 16 different uniformly random non-uniform sampling schedules. And when you have a uniform schedule, its Fourier transform should be uniformly random too. And that's what you see here. So the transform artifacts that are associated with a particular peak are uniformly distributed with respect to frequency, which is good. Now, any sampling schedule that departs from uniform random will have artifact patterns that are also no longer uniformly random. So for example, here's Fourier transforms of 16 different Poisson gap schedules. And you can see that the pattern of artifacts gets larger and larger as you get further away from a given peak. And every peak in the spectrum will have this pattern of artifacts. So what somebody who uses the Poisson gap schedule will argue is, well, look, you have less artifacts near your peak. Isn't that a good thing? And it's a good thing if your spectrum only has one peak in it, but presumably your spectrum has other peaks, and they will be out in these places where the noise contribution is larger. Okay, so it might be a wash to decide whether or not you get an advantage from one particular sampling schedule shape to another, but this will also depend on the reconstruction methods that you use and the nature, of course, of the actual decay in the corresponding data. Now, all these different cases of different reconstruction techniques and different schedules as a way to compare how comparable the results are. Here are volumes that are extracted from the peaks in those spectra from the uniformly sampled data on the horizontal axis, and all the different cases for the different reconstructions. And for reference, we also included a conventional reconstruction with linear prediction. And what we see is the uncertainties that we get in these volumes are predominantly dominated by just the uncertainty of being able to measure a volume from these spectra at all. So all of these reconstruction methods and reconstruction schedules produce comparable volume results, and they all produce virtually identical frequencies in both the proton and carbon dimension. And so now we move to a critical point, which is also kind of misrepresented and misunderstood in a lot of the literature, which is how many increments should I measure? What sampling density should I use for our particular spectrum? And it turns out that discussing this problem in terms of sampling density is not the correct way to consider it. Instead, we have to consider it in terms of the number of signals there are in the experimental data, in that the number of samples in our non-uniform sampling schedule has to be sufficient to describe that many signals. And then furthermore, we have the requirement for non-uniform sampling that the corresponding signal has to be sparse, which we can think of as meaning that the corresponding data has to have more empty space than peaks, as a rough approximation. Now, the behavior of non-uniform sampling reconstructions with respect to the number of signals has been studied by folks in David Donahoe's lab, including this result, which describes the ability to make a good reconstruction versus a bad reconstruction as a kind of abrupt phase transition, according to the number of signals in the data, such that for a given number of signals, the ability to make a good reconstruction drops precipitously once the sampling density goes beneath a certain amount. And we can actually illustrate that case. Okay, so this graph was derived from a set of simulations of the same data that started with 378 peaks, and we'll see the data in a little bit. And then we gradually reduced the number of peaks until only 5% of the total number of peaks was there. And we did reconstructions for these different cases with different non-uniform sampling densities. Now, the fully sampled data had 8,000 increments in the 3D data. And what we do in this graph is compare the RMS difference between a given reconstruction and an ideal version of that reconstruction. And the way we generated this so-called ideal version of the reconstruction is to make simulated data for one peak at a time and reconstruct that single peak data all by itself, and then add up all those results together to generate a final spectrum. So that ideal spectrum allows us to gauge the effect of the number of signals in the data on the quality of the overall reconstruction. And what we see is, if we plot the RMS difference between the reconstruction and its ideal with respect to non-uniform sampling density for these cases, the case with 378 peaks starts to get bad between 40 and 50% sampling density, whereas the 18 peak case stays good all the way down to 10% and 5% sampling density. So what's going on here? How can we explain this? One way to understand this is to assume that the reconstruction of a certain number of peaks is a little bit like trying to fit the data to a certain number of peaks. So for example, if we have 378 peaks in a particular 2D indirect plane, we can approximate the information content by saying each one of those peaks should have at least 5 parameters associated with it: 2 positions, 2 widths, and a height. So if we have 100 peaks to describe, that should be roughly equivalent to extracting 500 parameters from the data. Okay, so in this case, the experimental data had 8,000 increments, and each increment is complex in the 2 indirect dimensions. So that means the analysis that we're doing has 32,000 points to work from. And if we have a certain number of peaks, like let's say 100, that means 500 parameters to be extracted from 3,200 points. That's pretty reasonable. So what we can do to help understand what's going on is to plot the ratio of the total number of samples to the total number of hypothetical peak parameters. And when we do that, what we see for all the different cases, regardless of the number of peaks, we get a transition that seems to happen at around 10 or so. So in other words, we want about 10 degrees of freedom for every parameter that we're trying to extract from the data, which is not a remarkable circumstance, right? That's probably about what you would guess. So generally speaking, we're going to want about 5 or 10 times more samples than there are peaks to describe in the most crowded region of the data. And we can see that in this animation. So these animations are data with different numbers of peaks and slowly reducing numbers of non-uniform sampling densities. So now 75%, 70%, everything looks good. 65%, 60%, 55%, 50%, 45%, 40%. Now below 40%, this data with 378 peaks starts to look bad. 25%, now this one starts to look bad. 15%, 10%. Now this one looks bad. So by 5% sampling density, these three cases are garbage, but the case that has only 18 peaks still looks good. All right, so it's a clear relationship between the number of samples that you generate and the complexity of the data that you have to reconstruct. So, nice example. Finally, we're going to look at 2 or 3 ways that these non-uniform sampling methods can be repurposed for other applications. Okay, as we've mentioned, there are some things that are easier to do in one domain versus another. And if we go back to our description of the Fourier transform, what we know is that a point in one domain corresponds to a Fourier term in the other domain. So in the case of the time domain, the first time domain point corresponds to a 0 frequency Fourier term, which is a straight line. The second point in the time domain corresponds to a 1 period Fourier term. The third point corresponds to a 2 period Fourier term, and so on. So what does this mean? It means that when we have a baseline distortion, which extends throughout the spectrum, that this baseline distortion is actually caused by distortions in just the first few points of the time domain data. So we can take a case like this. This is 1D carbon data, metabolomics data, that was given to us by Professor Art Edison. We can use these non-uniform sampling methods to replace the first several points in the time domain to take data like this that has a baseline roller coaster and make nice flat data like this. And then finally, I'm going to show one application from our lab that was developed by Luke Arbegas there, called Sierra, which is a combination of a pulse sequence method to suppress signals in an NMR spectrum and a mathematical method that uses non-uniform sampling reconstruction to numerically suppress signals. Okay, so in our lab, we study protein therapeutics like monoclonal antibodies. And these protein therapeutics are meant for injection, and they are usually mixed with different excipients so that the protein will stay stable, not aggregate, not unfold. And the challenge for those of us who want to study these materials by NMR is that the excipient signals are often much stronger than the spectral signals that we're trying to observe. So here's our beautiful proton carbon methyl spectrum of a monoclonal antibody at natural abundance. And here are excipient signals. So 1, 2, 3, 4 polysorbate signals, and here's histidine over here. So we'd like to be able to get rid of these signals so they don't interfere in whatever it is that we want to do to the protein parts of the spectrum. Luke Arbegas invented the Sierra filter, which uses cross-polarization so that you can do doubly selective suppression of individual peaks according to their proton and carbon chemical shifts. And we can do it over a window that's about the size of the coupling constant between proton and carbon. So it's very nicely selective indeed. And we can apply these filters one at a time to each region we'd like to suppress. And when we do that, on this particular case, we suppress these 4 different polysorbate regions. And in this case, we can reduce them to 10 or 20% or so of their original intensities. And so we took this as a starting point and said, okay, this is a beautiful experimental suppression. Okay, and I think we see a question. Would you like to ask your question out loud?
Yeah, so this means that for suppressing 4 or 5 of these regions, you do the experiment and the reconstruction you basically take the spectrum like 5 times with a different region that you're targeting for the suppression each time and then combine them?
That's a good question. So what's done is that we have a block that we append to the pulse sequence. And one version of that block suppresses one region of the spectrum. And the parameters of that block are tuned to suppress that particular region. So if we want to suppress 4 regions, we add 4 versions of that block to the beginning of the pulse sequence. Okay. So we don't conduct 4 different experiments. We just have 4 initial stages of the pulse sequence that suppress each of these 4 regions in turn. Does that make sense?
Yes, thank you very much. That makes a lot of sense.
Yeah, thank you. It's a good question. So this is how good we can do with the experimental methods, and we wanted to see what can we do experimentally. And I'll show you what we can do numerically now. What we can do numerically is use the SMILE method to build a model of the entire spectrum and just isolate the parts of that model that correspond to the excipient peaks that we don't want, and then we can subtract them from the data. So we can go to a spectrum that looks like this, which is pretty awesome. And actually, okay, my mistake. I think I clipped out the animation that shows how this works. How strange. Okay. Pardon me. Gosh, I feel like the dumbest person in the world.
Frank, we have a question.
Yes.
Oh, hi, Frank. So the SMILE reconstruction you showed to just subtract the excipient data. So this is done on a fully sampled data or non-uniformly sampled spectrum?
That's a good question, and I will explain it in just a sec as soon as I find the.
Thank you.
Okay. There we go. My apologies. So the way SMILE works, and it works the same way for conventional data as non-uniformly sampled data. Whatever the largest signal that's left in the spectrum gets approximated as an ideal time domain signal that's Fourier transformed into the frequency domain. So for example, we start with a signal that looks like this in the Fourier transform of the data. And the largest signal that's left in gets approximated by this synthetic signal here. That gets subtracted from the data to generate a new residual. And the procedure is repeated over and over again. We generate a new synthetic peak, subtract it from the data to build up a model. And we keep doing this until the residual is empty, or as empty as we want it to be. So we can approximate any kind of complicated multidimensional line shape in terms of the sum of many different ideal line shapes. So this method absolutely does not require that the experimental data consists of ideal line shapes. Whatever line shapes the data consists of, SMILE will use the appropriate number of basis set functions to decompose that into something that matches the experimental data as closely as possible. So this can be performed on either non-uniformly sampled data or conventional data. And in practice, SMILE builds a model like this for the entire spectrum, and all we do is extract all the signals in a particular region to generate our synthetic data that gets subtracted. So that's the overview. We've seen ways to reconstruct non-uniformly sampled spectra that can be applied to both conventional and NUS data. We've seen some ways that those methods can be repurposed for other applications like baseline correction or signal suppression. And we've also seen some important facts that choosing the non-uniform sampling parameters depends importantly on the number of signals that there are to reconstruct in the data. So it's not strictly appropriate to talk only about the sampling density without also talking about the spectral complexity. So that's my overview. I hope it was interesting. If there are any other questions, I'd be delighted to hear them. And here's where you would hear thunderous applause in another presentation.
Frank, that was absolutely brilliant. Unbelievable. Thank you for sharing that. It looks like you do have a couple questions if you'd like to call.
Yes, let's hear the questions.
All right, Andy, you want to go first?
Yeah, Frank, can you hear me?
I can, yes.
Okay, so in the SMILE subtraction or modeling, if you will, of an artifact,
Yeah.
do you apply it to just a single spectral region, or does it get applied to all the vectors, let's say in a 2D, to all the indirect vectors, or do you just restrict it to one band where that peak occurs?
Right, that's a great question. So what we do, Andy, is SMILE builds a signal table, and we take only the signals from the regions that we want to suppress. But those signals are used to generate a spectrum that extends over the full spectral width in both dimensions.
Nice.
So we're not just subtracting data from one particular region. And let's see, to try to understand that a little better. So you see, like in this case, we would only extract signals from this region here.
Your
But when
pointer's
we
not showing, but
simulate
let's say,
them, yeah, when we simulate
Yeah.
them, those signals will have tails like this, and they'll be subtracted from across the whole spectrum. Does that make sense?
so you build a model, let's say the peaks in the left-hand side, that what looks like two large peaks that are
Yeah.
a little, well,
Histidine.
they have a phase distortion. Yeah, okay.
Yep.
So you model that, but you include that in the reconstruction of the full spectrum?
What we do, let's see.
It's kind of interesting.
This is
Yeah, so this is your, yeah, okay.
Yeah, so we actually make this spectrum. And this spectrum is made from time domain signals that describe all of these. And we Fourier transform them just like the regular data to generate a spectrum like this.
And then do you subtract the time domain from the actual data? Is that
We
what
subtract the frequency domain.
Okay.
Yeah, we subtract the
cool.
frequency domain.
All right, clever. Do you have a script that drives this?
We do indeed.
Okay.
It is,
All right.
it is very simple too. Let's see, maybe I actually have it here.
I'll put a plug in for Luke. The Sierra thing is very cool. We use it too.
What did you use it for?
Similar stuff in very different systems, but in the same kind of concepts.
Right. Anyway, the command to apply this signal subtraction is a single processing command.
So it just goes right into your
the
script.
name of the spectrum and the regions. It's called
Yeah,
basic
so you have
Sierra.
to, you have to define the XY frequency coordinates of the,
Yes, exactly.
the region, let's say an ROI that you want to wipe out. Okay.
Correct.
Cool.
So,
All right.
let's
Thank you.
see. Maybe I can even find it.
Frank, I would have a follow-up question on exactly the same thing. Can you hear me?
Yeah.
Yeah, basically when you create those 4 peaks, you need their frequencies. But for example, let's say they're completely dispersive mode, which introduces a little bit of frequency error. I imagine the script takes care of that. Looks in a neighborhood.
Right. So when we're not trying to extract frequencies, we are trying to approximate the shape of the spectrum. So we don't really care about the frequencies of the individual signals in the signal table, just that when we add them all up, they approximate the shape of the data.
I see.
So you're kind of fudging that through the iteration, just cycling through until find you a better set of summations that works, gives you a lower residual.
That's exactly what it does. Yeah.
All right, cool. Thanks, Frank.
Yep.
Frank?
Good questions. Thank you. Anything else?
Yeah, hi, Frank. I have a question.
Yep.
Rajan here. So this interesting and very important observation, conclusion, I would say, sampling density, it depends on the number of actual resonances rather than just the simple thought that more number of sampling density will give a better result. So a priori, when I have to run the news for a 3D or 4D data, obviously I want to do 4D because I don't have the time to run the 4D to determine how many peaks are there. So can you therefore say heuristically the sampling density I should choose for a news experiment is kind of proportional to the molecular weight or something?
That is a very reasonable kind of assumption. And most all proteins have the same density. There are a lot of things that vary about proteins, but they all have just about the same density. And so if there are NOE experiments, you can kind of anticipate what the most crowded region of your spectrum is going to look like. Right. And of course, if you have a spectrum that's just metal label signals, you can guess an upper limit for how many NOE peaks you could possibly see at any location also.
I mean, if I could,
I would say that you can probably, from the type of spectrum and protein that you're measuring, you can make a very good guess about the
density
expected complexity.
Yeah, if I could interject, this is something that I think Adam will touch on a little bit more.
Okay, good.
Frank alluded to something. It's not only the complexity, but the dynamic range is something that also has this profound impact on how much sampling is needed to get an accurate reconstruction. A nosy spectrum is a particular challenge because of the higher dynamic range in nosy than you would get for, say, a coherence transfer experiment.
Okay. Awesome.
Thanks for the comment, Jeff, although I don't quite dig into those details in my presentation for today, so that's a good conversation to have here. At this point, we've gone over by a bit for the morning, so if there are no objections, I think I'd like to wrap up this session now and thank Frank again. That was really a tremendous presentation, Frank.
Thank you.
A lot of hard work went into those animations and explanations, and I think that's really a gem for the community to be able to go back to these video streams and see what's in there.
Thank you so much.